In today's GCSE video, I'm focusing very heavily on the Edexcel 9-1 physics topic of space. So we're going to be looking at various definitions such as what is a galaxy, define the universe, what is the order of the planets within our solar system, and then we're going to be moving on and looking at things like the geocentric and heliocentric models of the universe and the life cycle of stars. So quite a lot to be getting on with. So let's start by looking at the solar system. So the solar system contains all the planets that you guys have heard of, and in order, starting closest to the sun, you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and sometimes people count Pluto, but I don't think we're supposed to count it anymore because it is too small to be counted as a planet. You saw me doing my thing of remembering this. The way I remember the order of the planets is my very easy method just speeds up naming, and that is a great mnemonic for helping you remember the order of the planets. Now, more terminology, we need to look at things like the galaxy. A galaxy is made up of billions of stars, so it's a collection of billions of stars. What is the universe? Well, the universe is made up of billions of galaxies. So we on Earth are living on a teeny tiny planet which exists in a galaxy. The galaxy you do need to know the name of, it's the Milky Way, and the Milky Way is just one of billions of galaxies which make up our universe. So yeah, it's kind of mind-boggling. I try not to think about it too much because it freaks me out. So we know that the various objects in space are held in position due to the gravitational force. However, what does the size of that gravitational force depend upon? Firstly, the mass of an object. And this is why the gravitational force on Jupiter is much greater than that on Earth, because Jupiter is so much larger, it has a way bigger mass compared with Earth. And secondly, it's the distance between the objects. So the closer the objects are, the greater the gravitational force. So we've already touched on it, but what is that gravitational force responsible for? So it causes moons to orbit planets, planets to orbit the sun, artificial satellites to orbit the Earth, and lastly, comets to orbit the sun. And try and remember that comets have very elliptical orbits. So if this is the sun, the comet's orbit is incredibly oval shaped. It's not really circular at all. We call this shape elliptical, and the comet travels fastest when it is closest to the sun. And that's all to do with that gravitational force being stronger, which we mentioned above. When the comet's further away, such as this point over here, it will be travelling far slower. Just to touch on one more thing, so looking at moons and artificial satellites. A satellite is any object which orbits a planet or the sun. So let's make a note here. And there are two categories: artificial, so ones that we put into space, and natural. And that's why I've highlighted moons, because these count as natural satellites. The next thing we need to look at is quite a complicated part of the specification, which is why does a satellite's velocity change even though it travels at a constant speed? And that kind of sounds like you're arguing with yourself, but you do need to know the difference between speed and velocity here, even though they sound like the same thing. So the real difference between speed and velocity is whether they're scalar or vector quantities. So speed is a scalar quantity, velocity is a vector quantity, and a scalar quantity just has a size or a magnitude. Whereas a vector quantity has both a size, so the magnitude, and a direction, and that's key. So although you could have a car travelling along a road, we know that drawing is not my strong suit, we could say that its speed is 10 miles per hour. So you could also say, because velocity also has a size, you could say that its velocity is 10 miles an hour. But to make it into a proper vector quantity, we need to say it is travelling at 10 miles per hour in a northerly, is that a word? Direction. Or you could say to the left. So notice, in order for it to be a vector quantity, such as in the case of velocity, it needs both a size and a direction. So going back to our initial question, which I'll write out again. So why does the satellite's velocity change even if it is travelling at a constant speed? This is because the satellite constantly changes direction, because it's moving in a circle, despite the fact that it is travelling at a constant speed. Hence, its velocity is changing. Next up, let's consider our historical models of the solar system. So, in today's modern day world, we understand that we have a sun that forms the middle of our solar system, and then orbiting the sun is a collection of planets, which I'm not really going to be able to draw, but we know the planet closest to the sun is Mercury, followed by Venus, Earth, Mars. So my very easy method just speeds up naming planets, and that these are all orbiting the sun. So they go round and round in circles with their slightly elliptical orbits. Notice that they're nowhere near as elliptical as our comet. So if we were to look up, you can see how incredibly squashed that circle is for the comet. Planets have far more circular orbits. So this is the modern day model of the solar system. We call it the heliocentric model. It puts the sun in the centre of our solar system. And the man who was responsible for this was called Copernicus. Great name. This is why I think I'm not going to achieve anything in particular, because I don't have a great name. Think about Einstein, Hawking, Newton. Maybe I'm imagining that they have great names, but they sound great. Lindsay, less great. Okay, so Copernicus, the reason why he was able to come up with this model is because he actually could see what was going on. So he used telescopes to suggest the new model. And today our telescopes are even stronger, and so we've actually managed to prove that his model is correct. So historically speaking, what was the other model of the solar system? Well, it was the geocentric model. And as you might imagine, because we had no evidence to the contrary, we put ourselves as humans on Earth in the centre of the solar system. So this puts the Earth in the centre of our solar system. And the reason for this really is because we were basing all our judgments on what we could see with our naked eye. And because our naked eye really can't see very far, we couldn't actually see other features of our solar system, so we weren't able to observe asteroids, moons of other planets, very distant planets, so ones like Neptune. And to name someone who actually thought that the geocentric model was correct, Ptolemy, what?
Ptolemy.
And Martin tells me that Ptolemy I can't say it is the guy responsible. Is that a silent P right there? Let's now look at the origin of the universe. What a statement. Origin of the universe. And there are two theories you need to be aware of. These are the Big Bang theory and the steady state theory, and we're going to summarize these now. So the Big Bang theory is probably the one you're most familiar with, and that states that the universe is expanding after exploding suddenly in a huge explosion, which we call the Big Bang, and it means that the universe started from a very small point and that space, time and matter were created in the Big Bang. I'm going to write that down now. Whereas the steady state theory suggests that the universe has always existed, that it continues to expand, and that matter is continuously created throughout time. Notice that there is a similarity in these, in that in both theories we state that the universe is expanding, it's just the beginning of the universe is different. So let's highlight the things which are the same for both. While they both state that the universe is expanding, the difference is to do with how matter was created. So what evidence do we have for these? Well, it's split broadly into two categories. So evidence, number one is redshift. Number two is CMBR, which is cosmic microwave background radiation. So let's take each of these in turn. So redshift is quite a hard concept to understand, but basically because we think that the universe is expanding, it means that we think that distant galaxies are moving further away from us. So if we're stood on Earth over here, I'm going to pick one star in one galaxy over here, and remember the stars are luminous, they emit light which can be picked up by telescopes on Earth. Now, according to the fact that the universe is expanding and that the galaxies are moving away from us, hopefully you can see that this star would end up in a new position further away. Now, if the light being given off that original star has a wavelength of something like this, are you happy that when it moves further away that wavelength gets stretched? So it has a longer wavelength. And if we were to look at the spectrum of colours, when you have a longer wavelength, it means that the light emitted is going to be redder. Hence why we describe this as redshift. So the light has been redshifted. So really, redshift provides evidence that the universe is expanding. So redshift can be used to support both the Big Bang theory and the steady state theory. And this is really important that you realise this. So both of these theories can be supported by redshift. Looking now at CMBR, so we've already said that this is cosmic microwave background radiation. It's detected in all directions in space. It has a constant temperature of approximately -270 degrees Celsius, and it's thought to be the remains of thermal energy from the Big Bang spread thinly across the whole universe. Now, as you might imagine, because we've mentioned Big Bang in CMBR, hopefully you can see that the Big Bang theory is supported by both redshift and CMBR. Because they do like to ask you about this. However, CMBR does not provide evidence for the steady state theory. We now need to look at the life cycle of stars, both very large stars and stars which are smaller, like our Sun. First of all, we need to understand the term nebula. Now, a nebula is just a big cloud of dust and gas, and that's the beginning of a star's life. We're going to take a small star to begin with, such as our Sun, and we're going to look at its life cycle. So to begin with that nebula, that big old ball of gas and dust needs to be brought together. How? Through gravitational pull. So it pulls together all that dust and gas, And then at that point it can start burning fuel, and the fuel in question is hydrogen, because the hydrogen nuclei come together. We call that nuclear fusion because they're fusing and they release a huge amount of both light and thermal energy. At this point, the star is in its main sequence. It's like the adult part of its life. It will eventually run out of hydrogen fuel and it will start burning helium, and then it will swell up to form a red giant. Then at this point it turns into a white dwarf, and then when it totally runs out of fuel it will turn into a black dwarf. Large stars, so very, very large stars, have a slightly different life cycle. They start in the same place, which is that they have a nebula, so the huge dust cloud, gas cloud, will be pulled together through gravity. Then it will enter its main sequence and will start burning through its hydrogen fuel. Again, nuclear fusion is occurring. However, this time when it runs out of fuel, it will turn into a huge red supergiant, and then at this point a huge explosion occurs called a supernova. I love that word. And then dependent on the size of the star, it will either form a neutron star, and if the star is very, very massive, it will form a black hole, which you've probably heard of from films. So how do scientists observe the universe? Well, that's through use of telescopes. We've already pointed out all the issues with using our naked eye. Honestly, really, with our eyes, we can't really see anything. So what are the 3 types of telescope you need to know about? Well, firstly, it's optical telescopes. The second is the radio telescope. And the third one is the space telescope. So let's have a look at each of these. So the optical telescope, to do with optics, so we're looking at light. So it's used to observe visible light from space. They tend to be quite small, which enables everyday people like ourselves to observe the night sky relatively easily. And for people who aren't particularly skilled in this field, we call ourselves amateurs. So it allows amateurs to view the night sky relatively easily. And crucially, they can only be used at night because they're observing light being emitted from stars in our galaxy. And their use is affected by poor weather conditions. So if it's foggy, you won't be able to see anything. Or if there's a lot of light pollution. Radio telescopes, as the name suggests, are used to detect radio waves coming from space. They can be used in all weather conditions. They're very large and expensive, as you might imagine. Things which tend to be more technologically advanced do gain a lot in terms of how much they cost. Lastly then, space telescopes. Hopefully you can see we're getting more complicated. Now what you find is that objects in the universe emit electromagnetic radiation such as infrared rays, X-rays, gamma rays, and although these are often blocked by the Earth's atmosphere, they can be detected by telescopes which have been placed in space, so in orbit around the Earth. I said quite a lot there, so I'm going to write it all so you can actually see it written down. Running out of space here, so I'm just going to carry on chatting about space telescopes down here. So they can be used to observe the whole sky. They can be operated both during the day and night. Clearly they're going to be very expensive and they're actually quite difficult to set up. And because they're in orbit in space, we can't go and fix them if they break. Only astronauts can fix them. So properly trained space people. So we've compared the three microscopes, the optical telescopes, the one that we'd use to observe the night sky, radio telescopes, and all the way up to space telescopes, which are the most technologically advanced. We've seen there are lots of disadvantages with the optical telescope. The fact that they can only be used in the night time, the fact that they're affected by poor weather conditions. But how could we improve the picture produced by an optical telescope? Well, we could use a wider aperture. That's all to do with the width of the lens. You could use a better quality lens and clearly pick the best conditions to actually use it in. Not that you'd do this, but if you actually went to a desert, you'd be more likely to see the sky more clearly because there'd be less light pollution. I'm going to write that here just for completeness sake. And now we're going to look at some past paper questions because this topic is quite tricky and I want you to see the sort of questions they're going to ask. 2a. Scientists no longer accept the geocentric model of the universe, but it was the accepted theory for hundreds of years. Explain why the evidence available at the time supported the geocentric model. So what is the geocentric model? Well, that's the historical but incorrect model of the solar system, which is that Earth is at the centre. And as we know to be the case today, the Sun is at the centre of our solar system and all the planets and moons orbit the Sun. So, explain why the evidence available at the time supported the geocentric model. So why would people think that Earth is at the centre? Well, firstly because they had no scientific evidence. The only evidence they had is what they could see with their eyes. And what was this evidence they could see with their eyes? Well, it showed to them that the sun and the moons appeared to move across the sky in the same direction. And due to that, people thought that them sitting on the Earth meant that they were in the middle of the solar system and that the sun and the moons were just zipping past. B. The Big Bang theory and the steady state theory are two theories about the origin of the universe. The discovery of CMB led scientists to accept only one of these theories. Explain why redshift supports both of these theories, but that CMB supports only one of them. So we need to make some very basic comments, first of all, about what these two theories state and what they have in common. So you want to start by saying that both theories state that the universe is expanding. But that only the Big Bang theory states that there was really a beginning where there was a huge explosion which sent all the matter whizzing out into space. And so if we now look at our pieces of evidence, let's first of all take redshift. Now, light from distant galaxies is redshifted, which means it has a longer wavelength, therefore indicating that these galaxies are moving further away from us. So actually, the redshift theory does indicate that the universe is expanding and therefore supports both the Big Bang theory and the steady state theory. However, the CMB which is present has to provide evidence for there being a beginning, and that's why it only supports the Big Bang theory and it is unable to support the steady state theory. Oh no, haven't been concise enough, falling off the edge of the page here. C part I, a star with a mass very much larger than the sun. Okay, so what do we know about our various stars and, depending on their size, about their life cycles? So let's take a large star to begin with. So it goes through its main sequence, which is actually longer than that of a small star. And then it swells up to form a red supergiant, followed by a supernova, which is a huge explosion, and then either a black hole or a neutron star, depending on its size. However, a smaller star, such as our Sun, enters a shorter main sequence, swells up to form a red giant, but not a supergiant, and then a white dwarf, followed by a black dwarf. I do love these names. So let's have a look in these options. So a star with a mass very much larger than the Sun, has a longer main sequence than the Sun, and ends as a white dwarf. No, there's no mention of a white dwarf in my largest star notes. B, has a longer main sequence than the Sun and ends up as a black hole. Yes, that's definitely a potential. C, has a shorter main sequence. No, I already know that's wrong. D, has a shorter main sequence. No, that's wrong again, which is why the answer here has to be B. Which row has two correct statements about black holes? So a black hole is something which, it kind of really freaks me out, because basically nothing can escape it. Nothing at all. No light, nothing. Nothing. And that's why we can say that no electromagnetic radiation can escape. And if you have a look at what I have written in terms of forming a black hole, you can see that it comes from very large star going through its red supergiant phase, followed by a huge explosion. So let's have a look and see if any of these options match up with that. One thing I do want to point out is a nebula is completely wrong, because that's the very beginning of a star's life. So it wouldn't be a nebula collapsing. So that's why A is wrong. B, allows nothing to escape. Yes, that's true. A very large star collapses. Yes, that's true. C, allows nothing to escape. Yes, that's true. I've already said why it's not a nebula collapses, so C is incorrect. And then D, only allows electromagnetic radiation to escape. No, I've said even light can't escape. So that's why B is the only right answer here. You do need to know a lot about stars though. 3. Figure 2 shows some lines in the absorption spectra from 4 different galaxies, A, B, C and D, and from a laboratory source. All the spectra are aligned and to the same scale. So we've got A, B, C and D. Explain using figure 2 which galaxy is furthest away from us. Do notice that we've got this wavelength here identified, and that's because it's the only thick line, and really that's our reference point. We're going to be comparing the thick line on A, B, C and D. And the other thing to notice is which galaxy is furthest away from us, and that means is the most redshifted. Because remember, when galaxies move away from us, their wavelength effectively gets stretched like this. The wavelength is longer, and then if you look at these wavelengths along the bottom of the scale, you're looking for the longest wavelength. So which one is the most redshifted? And the longest wavelength you'll find towards the right hand side. It's the furthest right of these lines, which is why, I hope you can see this, which is why this is the answer, C, because it has been the most redshifted, and we're going to write about that now. Galaxy C is furthest away. Because it has been redshifted the most. And is therefore travelling at the fastest speed. Cool, and that is done. Part 2. In figure 2, the reference wavelength is shown at 390 nanometers. Estimate the change in reference wavelength for the light from galaxy D. So going back up, right, we have our reference wavelength, which is here. This is going to be hard for you to see. I'm just going to change colour. And it's moved to here. So you just want to use this scale to help you identify it. And if you have a look, you'll see that that is approximately 20 nanometers. But they would have accepted any answer between 19 and 25. Calculate the speed v of galaxy D. Use this equation. We've been given the speed of light, and just be really careful with your units because we've got nanometers up here, meters per second here. So actually, although they've given us the equation, we do need to just be a little bit careful. So I'm going to write the equation out. V equals c delta lambda over delta 0. C, we've been told, is 3 times 10 to the 8, so that's the speed of light. And according to this equation, we need to multiply it by delta lambda, which we've just worked out in the question above, is 20 nanometers. And then be careful, you need to convert nanometers to meters, and the way in which you do that is by doing times 10 to the minus 9. So we're going to pop that conversion in here, and then divide the whole lot by delta 0, which we know is 390 nanometers. So 390, and then we multiply that by 10 to the minus 9 again to avoid any issues with units, and we get a final answer which is huge. It's 15,400,000 meters per second. B. Figure 3 shows a photograph of galaxy D. The photograph is taken by a student at his home. State 2 ways that the student can improve the observation techniques so that the quality of the image is improved. Some of this will be common sense. So for me, that would be move your telescope to better viewing conditions. And that's actually why a lot of these satellites are found in deserts. There tends to be very little light pollution, very clear skies. So I'm just going to write, because I like this answer, move the telescope to better viewing conditions. E.g. in a dry desert. Something else you could say is use a better quality objective lens. Can you hear the ice cream man? It's not even warm. And if anyone's listened to my first chemistry video, you'll know there was a dog banging and a builder doing something else. London is so noisy. Something else you could have said is use a wider aperture camera or use longer exposure time while the telescope is locked onto a star.